So now we are going to use the concept of rate of change and slope and try and analyze a particular motion. In this situation, assume a child is playing with a toy car in the house. You've been given the displacement of the toy car as a function of the time. Initially, for the first 2 seconds, the displacement is increasing, which means the child is pushing the car forward. But after 2 seconds, the displacement starts decreasing, which can only mean that the car is now coming back towards the initial point, which means the child is pulling it backward. And then again, after a particular point of time, the displacement starts increasing. So the child first took it forward, backward, and then forward again. Now let's say we want to find the rate of change of the car in the first 5 seconds. What would you do? You would take the initial point to be the origin, the point at time equal to 5 to be this point, which would correspond to displacement 4. You would say total displacement is 4 meters, total time is 5. By the concept of slope, it would be 4 divided by 5 or 0.8 meters per second. So can you then conclude and say that the speed or the velocity of the car at every point in its journey was 0.8 meters per second? Definitely not, because we just saw that the velocity was positive for some part, then negative and then positive again, and the velocity was changing at every point in time, which means that what we actually have as 0.8 is the average rate of change across the entire interval, but it does not tell us what actually happened at every instant. Which means that rate of change can be classified in 2 ways. One is an average rate of change, where your initial change in your input is fairly large, the time interval is a lot, which gives you a delta y rate of change, a change in the output, and delta y by delta x is your average rate of change. When you shrink this initial input change and you make it very small, you make the interval very small and call it dx, that results in a very small change dy, which is true reflection of what is happening at that instant, and that gives you the instantaneous rate of change dy by dx. So whenever we refer to delta y by delta x, it refers to average rate of change where the 2 points are fairly far away, but dy by dx tells you about the instantaneous rate of change or the rate of change happening at each instant. Now we'll see how we can actually calculate this instantaneous rate of change. Until now, we have seen that for any mathematical curve, if we have 2 points A and B, the average rate of change between them is numerically equal to the slope of the secant joining the 2 points A and B, whereas secant is simply a line that cuts a curve at more than 1 point. Now we want to find the instantaneous rate of change at any point, say C on the curve. We know that to find rate of change, we need at least 2 points to create the delta. We also know that to accurately determine the rate of change at around C, 1 point needs to be before C and the other point needs to be just after C. So what we are going to do is we are going to take A and B and start making them approach C. You will notice that as we do so, the secant joining A and B now converges to the tangent to the curve at the point C. The tangent to the curve is simply a line that touches the curve at just 1 point. We will repeat this so you can closely observe how the secant becomes the tangent. From here we can conclude that the instantaneous rate of change is numerically equal to the slope of the tangent to the curve at any point, just as the average rate of change is equal to the slope of the secant joining any 2 points. So now our journey of calculus officially begins. Up till now, we've been talking about finding the instantaneous rate of change, which is equal to the slope of the tangent to a curve. This process is actually called differentiation in calculus, and differentiation is just another operator used to find the instantaneous rate of change. Every operator has a symbol, like addition has a symbol plus. Similarly, differentiation has a symbol which is d by dx. X over here is the input variable or the independent variable whose value can be changed, And the value that you write here is typically the function whose rate of change needs to be found. For example, if I write d by dx of y, I am saying that I want to find the rate of change of y with respect to x. The input variable could be another variable as well. It does not always need to be x, but you need to find the rate of change with respect to some variable. For example, if the function is x square, then I would be saying I want to find the rate of change of x square with respect to x, which is essentially the answer to if I change x by a small amount, by what amount does x square change? Now we know that the graph of y equal to x square looks somewhat similar to this graph. If I wanted to find the instantaneous rate of change, I would need to draw the tangent at every single point and then obtain the slope of the tangent, which cannot be done. Differentiation gives us a tool which directly gives us a formula in which all we need to do is plug in the value of x at which point we need to find the slope, and it directly gives you the value of the slope of the tangent at that point. Now let's see how we can get to this formula. We know that to find d by dx of x square, we essentially need to find the slope y2 minus y1 and x2 minus x1, for which we need 2 points x1 comma y1 and x2 comma y2. I'll take my original point to be any point x, for which the corresponding value of y would be x square, because the function is y equal to x square. Then I will shift x by a small amount dx, such that my next point would now become x plus dx. The corresponding value of y would then become x plus dx the whole squared. And for both of these points, I'm now going to try and find the slope, which is nothing but x plus dx the whole square minus x square upon x plus dx minus x. The denominator simplifies to dx. I expand this numerator and I get all of these terms. X square cancels with minus x square. I have 2x dx and dx the whole square remaining. Now dx is a very small value. To get to a better accuracy, I would take dx to be very small, which means if dx is really small, dx square would be even smaller. Squaring any number less than 1 makes the eventual number even smaller, which means I can neglect dx the whole square in comparison to all the other values. Now once I neglect dx the whole square, I have 2x dx divided by dx. Dx cancels in both places to leave you with 2x, which means d by dx of x square gives me the simple formula 2x. Now if I want to find the instantaneous rate of change at say the point x equal to 1, what do I need to do? Simply put the value here and my answer is 2, which means the rate of change at x equal to 1 is equal to 2. Let's say I take the point x equal to 5. What is the rate of change going to come out to be? 2 into 5, which is 10. Now first let's try and understand what this conveys. At x equal to 1, the rate of change was 2. As x increased, the rate of change increased. Can we also see that from the graph? Definitely we can, because originally the value of y was climbing slowly. The rate of change was less, but as x increased, the value of y suddenly shot up. This also says that as x increases, my rate of change increases by this particular formula. So now differentiation gives you a tool to directly obtain the instantaneous rate of change at any particular point on any function by simply following this formula. In the remaining topic, we'll also see certain standard formulae and we'll directly give you the answers to those formulae. The detailed derivations you'll be doing in classes 12.